All right, you should all see a little icon that pops up asking if it's okay to record. So you can just click continue. So hello everyone, my name is Sam Rickard. I am I guess you could call a student advisor. We're starting up a student committee for this PhD webinar series. And the goal of this series is really to provide students with a platform to share the excellent work they've been doing for their PhD, whether that be dissertation or some other project work that they want to present. And this gives students a platform to share that work with the other students in the community here in PacTrans, and gives a nice forum where we can have discussions to talk about these issues that are at the forefront of transportation and transportation engineering. You'll notice today that we are doing this in a Zoom meeting setting instead of a Zoom webinar setting. And we did this on purpose because we think that having the ability to turn the cameras on and to see the faces of the people that we're talking with really helps to facilitate the discussion about the topic that is being presented. So today that topic will be presented by Ruimin Ke, and he will be introduced by Professor Yinhai Wang, who is his advisor. And so I will give a brief introduction of Professor Wang, and then he, as I just said, will introduce the speaker today. So Professor Wang is a professor at the University of Washington in the Civil Engineering Department. He is the director of PacTrans and does lots of work at the forefront and cutting edge of transportation engineering. Most notably, he does significant work in the fields of AI and big data analytics. So without further ado, Professor Wang, you can go ahead and introduce Ruimin.
Thank you, Sam. Hello, everyone. Welcome to join the PacTrans PhD webinar series. As Sam mentioned, this is a new webinar series we created. Just want to offer a platform for PhD and recent graduates for PhD programs to share their research. And our goal is to make this an outstanding platform. It's not only constrained to PacTrans students, but also anybody who is conducting excellent PhD research could use this platform if their research topic is relevant to mobility. Today's speaker is Ruimin Ke. Ruimin joined the University of Washington Star Lab since 2014, and he completed his master's research and PhD research, both on traffic sensing. Ruimin's background is automation. He graduated from Tsinghua University, the best university in China, in my opinion, at least. He joined us and focused on using cutting-edge technology to detect vehicle and road user interactions. He applied for different kinds of AI approaches, try to capture the roadway events that may be relevant to traffic safety. I think this is a very important thing due to several reasons. First of all, US DOT always consider transportation safety as their top priority. Secondly, a lot of research efforts going on the artificial intelligence. In transportation area, there's a huge potential to apply artificial intelligence into practice and research. So the reason we pick up Ruimin as today's webinar speaker is due to his research work relevant to both very important things. And he has also published a lot of research papers. You could go to his Google Scholar website and find out his research publications. Ruimin will start his assistant professorship at University of Texas, El Paso this summer. So Ruimin finished his PhD, I think about several months ago. So everything is very, very new and refreshed. I hope today, whoever joined this webinar would get a good opportunity to discuss on the details of his research. I see actually in our participants, we also have PhD researchers, professors. If you recognize any PhD student conducting outstanding research, please recommend them to us, because this webinar series is by invitation only. We only invite outstanding researchers to share their research experience. This is monthly at this point. We'll see if we get higher demand. We may make it more frequent. And if we don't see enough good research, maybe we can also lower the frequency. So anyway, this is a great opportunity for PhD students to share their work, and I hope you enjoy today's webinar. Now, Ruimin, the floor is yours.
Okay, thanks, Dr. Wang. Let me share my screen first. So can you all see the screen? Okay, cool. First of all, thank you very much, Dr. Wang, for the introduction. And thank you, Dr. Mudong, Sam, and Cole for organizing this webinar series. It's a new series, and so honored to be here. So some of you may have seen my work. This is basically a summary of part of my PhD dissertation. Some of you may already seen the work. Some of you may have not. But anyway, I think this is another platform and another opportunity for me to share this topic and some of the work we have been doing at the University of Washington Star Lab. So very glad to interact with everyone. So the topic of my presentation or my PhD study is about real-time video analytics empowered by machine learning and edge computing for smart transportation applications. So about me, as Dr. Wang have introduced, I'm right now a postdoc at the Star Lab. And I got my PhD last year in December in the intelligent transportation systems at the civil engineering department at UW, and my master degree in civil engineering at UW as well, and my bachelor degree in automation at Tsinghua University. And I'll be joining the UT El Paso as assistant professor this fall, and I'm also recruiting students. So if you know anyone interested, please also feel free to recommend. And my research interest mainly lies in ITS and intelligent vehicles, smart infrastructure, AI, edge computing, and transportation data related topics. And about video data and cloud computing, as reported by Cisco, actually 90% of the internet traffic will be video or images. And data shows that the total data can be handled by the cloud. Right now it's about 20 ZB, but the data generated as a network edge, including all the devices, sensors like your mobile phone and like other sensors, for example, in transportation, the loop detectors, the some other sensors, video sensors, the total data generated at the edge is like over 800 ZB. So we can see there's a sharp contrast between those two metrics and the need for new computing services for video analytics. So the edge computing is kind of emerging concept. And basically it's about computational processing of sensor data away from the centralized node or centralized cloud and close to the logical edge of the network, like where the data is generated. For example, you take a video at your on your mobile phone, and then you process it on your phone instead of transferring it to some server or some services for processing. And that's intuitively like what edge computing does. And it does have a lot of advantages. It reduces the internet bandwidth usage and reduce the computation load at the centralized cloud server. And due to the first two reasons, it's also friendly to large-scale data services and has a better privacy protection by not storing the raw data, because we have already processed the data, for example, images with a lot of sensitive information. We don't store the images at the cloud. So has potential for better privacy protection. And in the intelligent transportation systems world, we know traffic camera has been installed like almost everywhere, every city, and it's filling up a big gap in today's sensor needs. We see like on the top corner, there's the screenshot from our Starlab DriveNet system showing the WatchDot camera distribution in the Washington state, and that's only for the freeway cameras. And some places in China, we sometimes saw there's more than like 10 or 20 cameras at one intersection for the monitoring or enforcement purpose. And on vehicles, there's also many cameras. Like our private vehicles, we have our driver recorder, and on the transit buses for liability purpose, they have like over 10 cameras on one transit bus for recording. But how can we turn them into sensors? Due to the great advantage of videos, their low cost, widely deployment, and the rich information in the visual data. And there has been a lot of example. So in the ITS world, using video processing like traffic flow detection, parking surveillance, collision warning, like some autonomous vehicle related topic, and curbside space management, and transit passenger detection, their motion or the count of passengers, and travel time estimation with vehicle re-ID. But technically, it requires real-time capability and high intelligence to achieve those ambitious goals right now and in the future. So these two criteria, they really motivates us to address the challenges. So we know there's trade-off between high intelligence and real-time capability. Like in any algorithms, methods, computations, if we require high intelligence, usually the efficiency is lower. And if we want the algorithm to be simple, it can be faster, but usually less powerful. So to achieve high intelligence, we know there's machine learning like techniques right now booming, and many of them are for the purpose of achieving high intelligence. And for edge computing device, so as we mentioned, they can support the like processing data at the edge, but those devices, for example, your smartphone, and they are usually computation or energy constraint. So there's computation and energy resource constraint. So you may not be able to, let's say, you have a very powerful algorithm running on the Amazon Web Service, but you may not be able to run the same algorithm on the edge computing device. And for video data, so basically it's a 2D array of numbers, like showing here on the right and top right. It's basically a matrix. And the video data is in large volume and require high computational cost. And also for the large amount of video, there's a demand for low latency. So the video data, some Microsoft researchers call the video analytics or real-time video analytics the killer app for edge computing. And that's really some emerging or challenges, some headaches for the community, but also there's opportunities. And for there's another concept on top of edge computing is edge AI. So that means we achieve the some artificial intelligence functions on the edge. And right now we do most of the training of the AI classifiers, detectors, or other methods on the cloud, and then we deploy those on the edge computing devices. But in the future, we do expect all the training and testing being done on the devices itself. And the motivation and benefits for edge AI is the data generated at the edge need AI to fully unlock their data potential. And the edge computing is able to prosper AI with richer data and application scenarios. And the AI democratization requires edge computing as a key infrastructure. And edge computing can be popularized with AI applications. And the overview of actually my dissertation study. So on the video analytics, I divided them into 3 parts. So on the smart infrastructure, intelligent vehicle, and also the aerial sensing for road traffic. And the reason for that is we know ground transportation systems, they contain 2 major components. One is the road user, the traffic, pedestrians, vehicles, trucks, bicyclists, and another is the infrastructure, like the roadway, the parking facilities, and even others like the street light, those all the infrastructures. So that's how I divide it. And aerial transportation is an extension of the ground transportation systems. Right now, we have seen some like delivery or sensing or enforcement tasks, like right now by different companies and institutions, aerial transportation. And methodological perspective on the infrastructure, surveillance video has a fixed background, and for vehicle onboard video and area video, their video background is moving. So from an image processing perspective, the method we can use for them are different based on those properties. So from those 2 angles, that's how I divided my dissertation study. So I will give some of the examples, like the projects we have done. I mainly talk about the video processing work. So credit to all the collaborators and Dr. Wang and the Starlab colleagues. For example, this one, we collaborated with Norway Public Road Administration and like Bellevue and those sponsors. We developed this master sensor. So I was mainly taking care of some video detection task. And here you see the this first work. We do road detection and traffic detection and road surface condition classification. We collected images from the WatchDot API. We collected a lot of them, and we have our students labeling those images to like dry, wet, or snowy conditions. And for the traffic, we do like the road detection using vehicle trajectories, because that's very efficient and intuitive, so can run in real time on the Raspberry Pi Edge device. And then we deployed some vehicle detectors to detect the vehicles. And there's a like a new pipeline here, so try to fully leverage the power of Raspberry Pi and also ensure real-time detection, but not introducing in detail here, given the time constraint. So this work, I'm gonna introduce it in detail. So that's a paper we published last year, sponsored by Sound Transit for parking surveillance with Edge AI. So in this project, we installed our sensors, the first version of master sensors on the Angle Lake parking garage in Seattle, and we monitor 16 parking spaces using 2 systems. One is outdoor, one is indoor. At that time, still Raspberry Pi version 3, and now version 4 is already available. And because there's no Wi-Fi, we configure a 4G T-Mobile data card for data transmission, and that's also going to be the case for many applications, especially in like suburban area. And this is overall system architecture. So the point here is like we do the some detection on the Raspberry Pi, the edge device side, and then we shifted other computation to the server. And we just transfer those intermediate results to the server instead of streaming all the videos. So this framework is able to run in for parking. We consider it's real time, and it can save the bandwidth by not transferring all the images. And with the bounding boxes, the object type, those detections on the server, we do some tracking and occupancy detection. So in that way, we split the computation load and satisfy all the requirements, but still able to achieve a very efficient detection speed. And first of all, we train a SSD mobile net using transfer learning with traffic surveillance data set called MyOTCD, published by the MyoVision. And so because you know the general pre-trained classifiers on the internet, you can download, use like Coco or VOC, those are for general purpose. But for traffic surveillance, we want to enhance the detection. So that's why we use this data set to enhance the traffic surveillance of detection ability. And after the transfer learning, you can see some more challenging, like small objects, those vehicles blocked by the branches or other vehicles at nighttime, those can be detected. But we found that for this detection task, in the real world is still not enough. So later we modified the system by adding a more traditional background modeling method. But because the SSD mobile net is still cannot run in real time on the Raspberry Pi, but this background modeling is very simple, can run in real time on the Raspberry Pi. So we can leverage the temporal information, so we can do tracking of vehicles, so we can identify which vehicles is moving, which is not, and this is we modify the tracking on the server. We do tracking on the server because the SORT tracking algorithm, it's a standard tracking like developed in recent years. It really only requires like the bounding boxes instead of all the deep neural network features. So that's why we can run this algorithm on the server using the intermediate results. And we modified this a little bit for the parking scenario. So some vehicles, they are moving out of the slot and then like move away. Sometimes they'll be lost because you look at the third column. So the vehicles, when it's like trying to change the direction, it get lost in the foreground. And then the enhanced reliability is basically for detection of occupancy in more challenging scenarios, like extreme lighting conditions and occlusion. So here we just play some like very actually simple rules using the two sets of detection. One is from the object detection using like deep learning, and another is from the traditional detection. And we combine the detection results, and because they're different characteristics, we can address some of the occlusion and extreme lighting conditions to improve the detection accuracy. And you can see the detection results here. On the top, it's the final detection results. And in the image, we just show the SSD mobile net detection results. And we found that even after our transfer learning, our fine tuning, our other rules, it's still like in the strong foggy condition or some sunny condition, there's glare or direct sunshine to the camera. It's the most challenging. And in cloudy and raining, it's okay, except in some cases, there's raindrops on the camera lens and it will block some view and there's no way to detect. But still in those like foggy conditions, with our combined detector, it can be improved a little bit over the SSD mobile net. And some occlusions can be detected and some will still be missed. And here is the occupancy, the data we collected for 1 week. We show how the data look like for the third floor and sixth floor, indoor, outdoor. So those data we expect they can be beneficial for transportation agencies and some DOT and the researchers. So that's on the infrastructure side. We mentioned another part is for the onboard vehicle video processing. And in my PhD study, I mainly focus on near crash data collection and from the onboard videos. So you may heard about near crash or near miss, and that's basically the traffic conflict. So that's not real accident, but that has the potential to develop into accident. So the reason transportation researchers agencies like near crash data is because it's in larger numbers than the real accident and collision. Because to do some safety related study or statistical analysis or machine learning, you need big data, right? You need more data, the more the better. So if you want to study an intersection, you may want consider using near crash data instead of just the accident data. There may not be so many over even like many years. So these are some of the previous studies literature on traffic near crash detection, from the University of British Columbia and the city of Bellevue. So we are also actually Dr. Wang and I think PacTrans is a partner for this Bellevue project and Microsoft as well. And for the vehicle based detection, I will introduce the more recent work. So this is, we call it edge computing system for real-time near crash detection of intelligent vehicles. And in this research, we try to develop a near crash detection algorithm. And the algorithm is insensitive to intrinsic camera parameters. So you can deploy it on like different vehicles. And also edge computing system architecture with camera, LiDAR, GPS, different sensors. And has potential for large-scale deployment. And the intuition behind the near crash detection is that we try to use the bounding boxes of vehicles, and when there's you see the vehicle is moving away from the ego vehicle, from the driver, the object's size or the bounding box size will decrease. And when it's staying at the same distance to the ego vehicle, the size will be the same. And when it's approaching the ego vehicle, the object size will increase. And that's for the longitudinal motion, and also for horizontal motion, we can get the information from the bounding boxes as well. Even though the bounding box is not originally developed for this purpose, but we found we're using multiple frames to do a regression. We can use that as an estimation for this purpose. Okay, and this is the system architecture. So here we implement this architecture on another edge computing device called NVIDIA Jetson. That's more powerful in terms of video processing and AI tasks than Raspberry Pi and other devices. Here we implement we implement SSD inception detection network, and as the first step in the main thread, and we can get vehicles and pedestrians and in real time. Actually, this is like faster than the SSD mobile net we just mentioned, but still it can get real time performance with the TensorRT optimization and so the JSON device. And then we play with the bounding boxes. We developed the three very simple but efficient linear regression models for computing the time to collision using the size of the bounding boxes and the horizontal motion of this using the center of the bounding boxes, and then several rules for determining if it's near crash, and several other thread like for the video frame reading, data collection, or data transmission. So when there's an event detected, we'll transfer all the data back to the server. So this is similar, so we don't have to stream all the videos back to the server. So we just detect the events we are interested in. So the definition of the interested events can be different from different tasks, but that's the logic. And also we talked to another LiDAR-based system developed by a startup company. This is a project funded by the Federal Transit Administration. And the LiDAR system talked to us and we communicated with each other. So we can get their events as well and label them and get it back to the server. And this is, we have already talked about the main thread, modeling, bounding boxes, and the TTC is very simple with some mathematical derivation. It's related to the size of the bounding box and the changing rate of the bounding box using like about 15 or 20 consecutive frames of regression. And so you see it's not related to the camera focal length and others. So you can run it with different camera without significant fine tuning. And one question we raised is, this is in more detail, do we use height or the width of the bounding boxes for the TTC estimation? So later we found that height is a better indicator because the width, it may not be completely related to the distance to the equal vehicle. The height does not really change, even you are turning, but as long as you are staying at the same distance, the height is the same. So we use height as the first, the main detector, but we also incorporate the width because in most cases, the width is still useful. So that's how we develop the double threshold rule for time to collision. And also for the horizontal motion, we do some similar thing and to estimate, because you see in those, if you are moving away from the vehicle in the camera frame, like those green arrows, we consider those are no like collision, and for others there might be, and we so some threshold need to be fine-tuned here and develop the rule. And we have implemented and done the over actually more than several thousand hours of tests right now. Like you see the device, those we tested on cars. This is my car, and also we tested on the Pierce Transit buses. And this is the cabinet where we install the system, and there's other systems which conduct some regular operation of the bus. And this is a short video showing some detection results. And you can see the bounding box, it's green, like when we detect vehicles or pedestrians, but it will turn red based on our detection algorithm when near crash is detected. And our algorithm is able to filter out some false detections, like in the previous video. You see there's a false detection. It recognizes something in the inside the vehicle as another car, but with the near crash detection algorithm, that can actually be filtered out. So those videos mostly collected from online sources. So we have no idea what's the camera focal length, but with the same system, we can detect those near crashes. And this is a video I took with my iPhone. So when I drive my car, I put this device on my car. And showing the real-time detection. And this is the pedestrian detection. We have our colleague Jill running towards the running towards the bus. So this is when we first among first several times we do the testing on the Pierce Transit buses, and this is more detection on the UW campus, around the UW campus, and showing like we collect the data we collect is like the GPS trajectories and the event locations. And these are the some more warnings, the events we collected on the Pierce Transit buses. And on the bus, we also add an auto boot up module because the Jetson TX2 device, it doesn't have a auto boot up function. So every time you have to push the button, but that's not doable if you leave the device there for running for a long time. And another part we mentioned is the aerial sensing for road traffic. And given the time constraint, I just summarize those work in one slide. And this is a recent paper also published last year. And you see this is from the UAV view, top view. We detect the vehicles and also the lane traffic, the road lane boundaries. So there's multiple different modules in this work for lane detection, vehicle detection, tracking, and traffic parameter estimation, both the macroscopic like speed, volume, and density, and also for each individual vehicles and headway, space headway, time headway. Yeah, and that's all.
Thank you, Ruimin. That was an excellent presentation. So now we are moving on to Q&A, and this section will be monitored by Professor Wang, who's introduced earlier.
Yeah, now you heard about Ruimin's PhD research. So you may have your own questions. I think as I mentioned in my recent LinkedIn post, PhD students are actually on the frontier line of cutting edge research. So they know all the details. You ask me how the model was estimated, I may not tell you the details. So feel free to unmute yourself and bring up your questions. Brandon, you have some question?
Yeah.
Good to see you.
Hi, everybody. Just to give you background, my name is Brendan Morris. I'm a professor at University of Nevada, Las Vegas, and actually my dissertation was somehow related to very similar things, although quite dated techniques at this point. I'm just curious, from your perspective, what do you see as kind of your next, where do you go from here? Like, what do you see as the biggest challenges right now? I mean, obviously you've done quite a bit of different things, but I don't know if you have an area that you're focusing in, or what you expect to be, what sustains you for the next couple of years here.
Sure. Thanks for the great question. So one thing I can think of right now is on this slide. So for edge artificial intelligence, right now, so the research community is still, we are on the like level 1 or level 2 to level 3. So we do the training those things on the cloud, and so the next step, I think one direction is we can try to shift both the training, like, and testing to the device. So for example, we may develop some new learning like mechanisms. So how about we update the classifiers or detectors while we collect more data on the device, and can we update the parameters or even the structures on the device while we may be able to, let's say, first we deploy the classifier, and then we update the classifier on the device, instead of we need to communicate with the cloud and redeploy it. That's one thing I can think of right now. And also, I think for the transportation, for transportation systems, like right now, those studies are all still, I think it's relatively small scale. And if we go larger scale, I do expect there's going to be many challenges we need to address, both from the scientific view and from the engineering view.
Any other questions?
Hi, Ruimin. Thank you for the great presentation. I have a question specifically on your parking lot study. When we do studies of movement of people, the big issue is, to get consent of tracking people. And I was wondering whether in the parking study, particularly, if you have problems with privacy because you're tracking individual cars that can then be tracked, linked back to actual people.
Yeah, great question, Dr. Mudong. So actually, we don't, as I mentioned here, so we don't stream the original, like the raw video data to the server. So we don't have the raw video data. So those data here I show the results, and that's for the research only. But for running the system, like here we have the results. But for running the system, we don't need those images. We don't need to collect any of them. So we don't know those, even though we do tracking. But that means we track the vehicle, we know there's a vehicle, and this is the same vehicle in the next camera frame. But we have no information what's the vehicle, and what is the license plate of the vehicle, and who's driving the vehicle. We have no idea. We just know here's the vehicle, and in the next maybe second, and in next 2 seconds, this is the same vehicle. And that's for the computation or detection purpose, instead of really like tracking the vehicle, the detailed information of the vehicle.
Let me also add something here. And Remy also mentioned the future will be edge computing. Edge computing has the advantage of information being processed as the edge device. You can consider if there's a sensor on site, everything is done within the sensor. So instead of sending back a unique identifier for a particular vehicle, or any privacy related information, you could just send the traffic data you need. So this particular research Ruimin is presenting is a combination of like on-site tracking. So we know if there's a vehicle there, how long the vehicle has been parking, but there's no license plate or any unique identifier information. So I think that's much better than a regular approach that will be recognizing vehicle's license plate.
I mean, I don't doubt it, and I'm not a specialist in that, but there's been studies showing that for data from like cell phone towers, all you need is like 3 or 4 points. I think the minimum, the maximum is 4 points. All you need is 4 points of GPS points to actually be able to trace back the user of the cell phone. I'm not, saying I can do that, but I'm just, there are studies showing that. And so, by tracking the same vehicle and getting, points, location points of that vehicle, it might be possible to then trace it back to individual owners.
Certainly, and I think privacy is a big concern. That's also something faced by traffic sensing researchers. Yeah, so license plate is pretty bad, for the privacy concerns. Bluetooth or Wi-Fi based MAC address sensing, that's also somehow relevant. You see a lot of phone companies has already protect, the MAC address by randomizing it. I think edge computing is going to be the future solution. That's going to be collecting the traffic information absolutely needed while minimize the privacy concern. Any other questions? So normally we schedule our PhD webinar for just 50 minutes. We're getting close to the end. If you have any question, please bring it up. Maybe one last question.
If nobody else, I have another quick question, hopefully.
Go ahead, Brandon.
So I'm just curious, you did on Raspberry Pi 3, and I don't know, you probably did Pi 4 as well, and then also Jetson. And I guess you use TensorFlow RT or whatever. I'm just curious your experience with that, because I've had some problems in the past trying to get models to work well when doing that. So I'm just curious, like how your performance changed once you went to that real the RT as like quantization or something, right?
Yeah.
What kind of drops in performance do you typically see?
So I think I didn't really like compare the before and after performance like quantitatively, like this increased by 100% or so. But I do see there's a large improvement on the efficiency side. So you said you had some problems. Did you mean you had some problem implementing or make it work, or?
I mean, it's been a little while since we were doing it. It was like a year and a half ago, but some of the models that we had, we were just trying to use like the conversion tools to take an existing network and then basically quantize it and go through that. And then there was just some issues when we tried to just go through the tools at the time. So I don't know, they might have improved. We just haven't done it in a little while.
Yeah, so for the Raspberry Pi, I used TensorFlow Lite.
Oh yeah,
So,
that's what we did too.
Yeah. I think that's probably what you used.
Yeah, that's what I was using. Yeah.
Yeah, so you can convert the TensorFlow models. That's basically doing some quantization.
Right.
And the Tensor RT, I think that's for Jetson. That's just for the Jetson device. And there's some other, I think, techniques we can use, and I believe you're aware of them. So for improving the network inference speed, like pruning and some other like combination of different techniques. And I'm exploring that, and our lab is also exploring that. I see like Yifan Zhuang is here, so he's also doing some edge computing research. So yeah, I think we can like give you more update and So keep in touch if that's okay.
Yeah, great. Thanks a lot. Appreciate it.
All right. Thank you very much, Ruimin, for your excellent presentation, and thank you all for coming and listening in and watching this presentation. So we will have another presentation this quarter for UW, for those of you who are at UW. So be looking for the registration link for that coming in the future. But yes, and I see that Professor Wong has put Ruimin's email in the chat. So if any of you have any questions that come up once this is over, feel free to use that. And without further ado, I thank you all for coming and have a good rest of your day.
Thank you, everyone.
Bye.
By the way, the next presentation is Washington State University.
Yes, that's correct.
Okay, on the 25th of May.
Okay.
Goodbye, everyone.
Thank you.